Hi, everybody. Happy, ugly Mr. Samuelus here. Oh, look at my daughter. All right, here we go. I'm going to make my kids cry at home, just like students here. All right, here we go. Good start. Okay, so we just ended with this one. I had this, I made a, note thing for them. So the first video of the day, all this is filled in on PowerPoint. So look at all the key things here. I do want to make a note. I don't know if Samuelus from last year said this thing right here, removing redundant edges, actually starts with a T. Anyone? Trees. So now you can go ahead and write this down, but we already have this, Mr. Samuelus. Okay, so we talked about weighted graphs in the first video. That was my PowerPoint, and now it's about trees. And you notice those last two pictures that I showed you from that PowerPoint, that those do look like this first one. All the vertices were connected, but there were no redundancies, no circuits. So the second one is not a tree. Don't worry about that too odd. I think back in the day I was making a point of something that means absolutely nothing. Okay, so now this first one. This could go a whole bunch of different ways, all right? But that looks like a three-dimensional cube, right? That's what I attempted to draw. Yes, Mr. Samuelus. Now what we're going to do is try to make a tree out of this. All right, so the first thing you need to do, just like similar when we were doing subgraphs and other questions, you got to draw the vertices. And I'm doing a real bad job. They're kind of scratchy. Okay, and then what I need to do is draw this so that there are no circuits, but all the vertices are connected. And I can get from one vertex to the other through some sort of edge scenario. I'm only going to do this once, so let's begin. Oh, we could start here. Those are connected. We could start here. Now I connected that vertex. Any circuits yet? Anyone? No. If I go down here, is that a circuit? Yes or no? Circuit? No. Okay, so now, the first thing I can't do is I can't make up new edges. Like, I can't do this because there is no diagonal listed on that one. So we have to use our original graph and make a subgraph that only has the original edges on them in the first place. All right, and then I'll just quicken this up here. What is this dot here? I kind of lost myself. This is the one in front. So can I do this and connect that vertex to that one? Yes or no? Do I have a circuit? The answer is no, so the answer is yes, I can. And then I could do one of two things. I could go down or I could go out like that. Now, if I add this one right here, which you can't really see my pointer, so I have to kind of draw it, that's a redundancy. I already have those two vertices connected with some other vertices, but also it makes a circuit, which is the general rule. Now, two have not played. All right, so this is not done. The tree is not complete because two vertices are not part of the graph. So how do I do that? It could be many different ways. I could do this, and then I could do this, and then I'm done. And that is one weird version of a tree. I'm not going to go through another one. I think online on the notes I have probably two different drawings from that, and there's multiple ways of drawing a tree where those rules are held intact. So I want to move on. Darn it! Let me erase that. Hey, in number 9 that I pulled out of the book, do you think letter A is a tree? Shucks. The reason yes is the answer is what is this not? That is not a vertice. So there is no circuit here. So each edge connects all the vertices. There is no redundancies. There is no circuit. So this is definitely a tree. What about the second one? Yes or no? Instantaneous answer. No. What screws it up? LNM. Okay, I'd have to remove one of those edges, and it could be actually any of them. Any of those three edges could be removed, and then I would have a tree. Any one of them. Because then all the vertices would be connected in some way, shape, or form. But it's not, so it's not. And then what about the last one, C? Oh, a discrepancy. Let's play Braveheart. The yes is over here, no is over here, fight. No one even knows that movie. The answer is no. What screws it up? BE is not connected. These are actually two separate graphs. Here comes a word two components. Remember that word from last week? All right, two different things doing a different function. So that's a no, not a tree. All right, then we'll get into the brass tacks of what we're going to do with the tree, but after this example. I'm not finding three. I don't have the time, nor do you want to watch. Okay, we're just going to find one. This is just like the box. I think I may have assigned 11 in the homework. So here's what you do first to make at least one tree out of this. Yoink, 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 yoink. Y, Z, A, B, C. So you don't have to write the question from the homework. The first thing you put on your paper are the vertices, and then you start copying vertices without making a circuit and making sure everything gets connected. And do not make up edges that don't exist. ZA is not connected. Okay, so it's not a connection. And I guarantee you this will probably be a different answer than I had the other hour. Look at how shaky I am. That's what this computer does to me. Okay. All right. Have I made a circuit yet? No, Mr. Samulus. Now I'm really kind of stuck. But I could do this. Believe it or not, I could go from Z and do those lines right there because I don't do a circuit, and yet I still have everything connected. But the way I want to go is I kind of like this one. Yoink, because that exists in that one. Actually, I'm a liar. I think that's the one I did first hour because it just makes me want to go that way. But if you listen to what I said about Z, a different way would just have those two lines coming from Z to C and B without that one going from A to B. All right? Take a pause because this isn't going to take too long. Okay, now we're going to do some math and put it all together because there was no weights on those trees. That's why this is a nice little bridge to the beginning of the notes to the end. Okay, so a minimal spanning tree throws the idea of a weighted graph and wanting to make a tree out of it. My first example does not have a real-world tie to it. The second one does, to give you an idea of why you would want a minimal spanning tree for a situation. And don't worry about this, but really consider only the vertices on your paper from your book. You just draw the vertices without edges. That's number one. That's what it means about considering the vertices. So just draw the vertices. Number two, step one. Okay, well, step one is, drawing the vertices, so I guess we'll call it step two. Select the smallest weights available. Whoops, I always do that. It's my fault, not the computer. Just want to make sure we were taping. And then step three. Keep selecting the smallest weight available, avoiding redundancies, avoiding any circuits, and keep doing so until all vertices are connected. That's really as simple as I can make it as far as what they say here. Okay? Now, you already have these examples. The first one is just a silly little drawing. The second one I'll refer to where it comes from in the book. It's an example in the book, and it'll tell you why you would do this. And there's other reasons, but this is just one example. Okay, so there's your question in the book. You're not responsible for writing this on your paper. What you're responsible for doing is just doing the question. I ask minimal stuff from you guys. I really, really do. Just want you to get the brass tacks. Just figure it out, because we're not doing some greatly challenging stuff here. We're just showing you some new things. You just got to follow the directions. And then there is a little point hiding in the middle, and I'm going to put that L right there, because if I do need one of those edges, I don't want it to run over. And I'm going to use my highlighter, but you don't have that option in your homework. But according to the rules, I have to select the edge that has the smallest weight. Now, these mean weights. They're not what you did before order when you moved around. So we got to get those differences in our head. What is the smallest weight available? 1. So I'm going to select that. I'm going to put it in my subgraph. This is how you do your homework, and you put 1 there. Not rocket science. What's the next lowest number or numbers? Are both of these allowed? Meaning if I select both of these, do I complete a circuit? Yes or no? No. You just got R into the game, and you got L connected into the game. All right, and there's no redundancies. So in your new graph, I think I changed colors. No meaning to that. Don't flip out on me. Okay, just randomly hit the wrong color. Everyone just calm down. All right, what's the next smallest number, everybody? 3. Now, is this 3 okay? Is this 3 okay? No. Okay. That creates a circuit. Okay, that 3 creates a closure from, and it's a redundancy because I have that 2. It's what is that called? I'm so bad at geometry. Parallelogram? Never mind, everybody. Okay, so could be a rhombus, could be a parallelogram. Let's not fight over it. So I can't pick that 3. Can I pick any of the 4s? Yes or no? No. So what's the next one that I have to pick? Okay, what's the next lowest after not being able to do this 3 that I'm pointing at? And both of these 4s actually close the circuit. So I have to pick, no, the next lowest is what? 6. And then what's the next lowest after that? Because really only one thing's not connected, and it's Y. So we ended up with those nice ones there. Okay, so I go back to this. Change colors again. 6. That moved on me. And then 6. Then notice I have a weird looking tree, but all the vertices are now connected. They're all involved. They're all in the network. You know, and as I write this down, then you write your weight. Another thing you might want to do this for is wiring. Wire costs money. So if I just need to connect these vertices with wiring, I'd want the least amount of wire to be used. So I'd want the shortest distance if these numbers means distance. 6, 12, 13, 14, 15, 16, 17, 18, 19, 20. So that connects all the vertices in the shortest possible way, guaranteed. All right, so I got us pause. What time? Pretty good movie. I feel like lawyers. Okay, so here's this situation. I won't read it for you. What I pulled is a subgraph, but I did want to insert it in the movie. Okay, a college building. Remember Truesdale sat behind? Actually, the guy sat behind that did this for a living for a college. Told you, and he flew in a jet to the Notre Dame football game. Well, here we go. But this is the problem. There's all these buildings, and they're kind of far away from each other. And there's been complaints about it being freezing. So what they do, okay, we're good. I swear to dog. Okay, all right. We had a little incident there. We want to build a walkway that is covered and heated. Just pay attention to the situation of why we'd want to minimize our costs. But we're not going to build a walkway that connects every single building. We don't have that money. We're going to give them an option, though, that there's at least a walkway that I have an option to go from one building through other buildings, and it's all connected so I can at least get from A to B to C to D, E in some way, shape, or form. But I want to use the least amount of materials, and also you have to keep it heated. Less space means less of a heating bill, so it's constant savings. So if you understand the question of why we want a minimal spanning tree. So somebody measures the direct distances to the buildings because we'll be able to build the walkway directly from one building to the next. So they get all this footage measured. Okay, now let's go to our notes. This represents that footage in a nice little graph. Okay, and it doesn't even have to look like that picture. The buildings don't have, they can be all cattywampus and look different. The only thing that matters is the lengths. Okay, so now I'm going to do this through highlighting, and you can as well, so I don't have to write the subgraph. Because the idea is we want the minimal amount of footage to get this to happen. So, what's the first edge that I select? What is the smallest edge, the two shortest buildings as far as distance is concerned? Say the number out loud. Hey, I can't help you in finding smallest numbers. You got to look at various answers in this 6 hour. 120 is the smallest number. All right. So that's going to be one of the connections. We're going to connect those two buildings. Okay, what's the next smallest? Be careful. 200. Now they're nervous about answering. 200 is the next smallest. So we're going to connect those two buildings. What's the next smallest? You don't have to be connect. Yes, it's 210. You don't have to stick with, okay, well, I got to stay with. No, just find the next edge that's legal to do without closing a circuit. This is not really a big concept here. What's the last edge that I will use that's the smallest and it's allowed? And then we could have done anything. It could have been this one if it was shorter. Doesn't matter because even that one you'd have a way to get from E to D. But that's 500, and we want to avoid that one because that's more cost in building and more cost in heating. The last one is that one. So that's how we're going to connect the buildings. So we do have an option. If I'm in building C, I can get to A or D, but I'd have to go this way. And that's what you'd have to do if you really want to be warm. And there would probably be signs all over. Don't use the walkway at your own risk. If you die from frostbite, that's your fault because we have a walkway that gets you the ability to go from one building to another, whether you want to do that or not. Do you understand what I'm saying? Because in these litigious times where everything is everybody else's fault, you have to have all your bases covered. Yeah. Okay, so I just thought I'd add that at the end. I did the wrong button again.